Hi guys, and welcome to a new Abaqus Isight combination tutorial. Today I would like to discuss about parametric optimization. Let's imagine you have a couple of parameters that controls your structure. You have a structure you want to optimize, and by moving some parameters, you will drive your structure. Parametric optimization is a discipline that will enable to find the best values for parameters that will give, in fact, an optimized structure. To illustrate this, I have a problematic to show you. We have a pump and we have a boat or a vessel, and we want to put the pump on the deck of the vessel. But the problematic for the team is to design and build a pump support, because we have a pump, we have the deck, and between them we need an interface, which will be the pump support. About the team, to explain you the context, we have workers on the vessel, and we also have engineers that we represent, and as engineers we need to design the pump support. And on the boat, the workers are able to build the pump support. And they have a lot of plates of steel with different thicknesses. So we will, as engineers, focus on that point to find the best design the workers' team will be able to build. So the pump support, and our problematic is to find the design and moreover the best design. And all the constraints will come from the workers. What they can build, what they cannot build. Okay, what will be the connections with the pump support? So first, between the pump and the support, we will have bolting connections. Bolting connections. Okay. Between the pump support and the deck, we will have welding connections. So let's talk about the design of the pump support. If I let you 10 seconds, can you spot a design to have a pump on the upper side and to be able to be welded on the lower side? Okay. The pump support is this structure, and by ref point here, in fact we will see later, but I can say 2 words about it. It represents the center of gravity of the pump, coincident with ref point. We have 4 couplings, we'll see why later, but our pump support is right here. About material, it will be in steel, because our workers have a lot of steel on the vessel, and it will be a high quality steel, and its yield strength will be about 345 MPa. About the connections, and just to explain our hypothesis, about the weld connections, we will have 4 pinned edges. So we have our pump support, and the pinned edges, there are 4, 2 longitudinal and 2 transversal. So 2 longitudinal and 2 transversal, which gives 4 pinned edges. So this is to model the welded connections. It's a little bit conservative, but for that model we have judged that it's enough for us, and we'll be satisfied with that hypothesis. About the bolt connections, 4 couplings from the pump support center of gravity to the bolts. So if we see a top view, we have the center of gravity at the center of the image, and the 4 couplings that we have seen previously will link the center of gravity of the pump, which will not be present in our model, to the pump support, and to, in fact, the 4 holes for the bolting connections. So here, 4 couplings. About the load conditions. First of all, load conditions, they are all located at the pump center of gravity. We will have the mass of the pump plus gravity, which will be applied to all the model, to the whole model. So the mass of the pump is 500 kilograms, and we also have loads Fx and Fy, pretty strong, 100 kilonewton and 50 kilonewton along X and Y respectively. All of this is applied right at the center of gravity of the pump. In our problem, the optimization problematic will be to find the best thicknesses for the pump support. By finding the best thicknesses for the pump support, we mean that as an objective, we want to make the pump support withstand the stresses. Absolutely. It is the most important part of our design, of course. But also, because it is an optimization problematic, we want, as a constraint, not to oversize or not to advertise too much the pump support, which means that we will be able to find the best design, or one very good design, to avoid waste a lot of material, a lot of steel, to avoid the make the pump support very heavy, etc, etc. So here at the pump support, in fact, we have three components. We have the main plate, the present thickness, the current thickness is 10 millimeters. We have two longitudinal stiffeners, so one here and the other one just behind. The current thickness is 5 millimeters, and we also have two transversal stiffeners, current thickness 5 millimeters. About optimization, three thicknesses as input, because three structures, so main plate, longitudinal stiffeners and transversal stiffeners. And as output, we will just focus on max von Mises stress. So as a scheme, we can see that the thickness of the main plate, the thickness of the longitudinal stiffeners, the thickness of the transversal stiffeners as input for Abaqus. Once the computation has been realized, we have as output the max von Mises stress. With that value, we'll be able to loop and to modify the values of the thicknesses and to make another calculation that will give another output, and so the optimization loop will look like this. And finally, about constraints, the following constraints we have to respect them. So allowable thicknesses for the main plate, we have 10 millimeters to 20 millimeters, one by one, so 10, 11, 12, etc. till 20. For both longitudinal and transversal stiffeners, we have 5 to 15 by step 1, so 5, 6, 7 till 15. An additional condition is that lower and transversal stiffeners thicknesses have to remain lower or equal to main plate thickness. This is an additional condition that we will call this condition inequality. So we cannot have, for instance, the two thicknesses at 15 and have a main plate at 11. This will not be a feasible design. About the output, the von Mises stress in MPa, so the maximum, as we have seen, the yield strength is 345. The target will be 335, so just a small margin without any safety factor, because we consider that our model is conservative enough. But the target will be 335, and we also set a minimum. This is to optimize our structure. And just to give you an idea, with our first design, which is 10 mm for the main plate, 5 and 5 for the stiffeners, the starting value of the von Mises stresses, the maximum is 965. So we have really overpassed the maximum limit. So we really have to find the best thicknesses, because for now our pump support doesn't work and even doesn't withstand the stresses. The pump support has been designed in Abaqus CAE, So we can see the part. As properties, the material is steel, and we have 3 different properties to separate the main plate, the longitudinal stiffeners and the transverse stiffeners. So as we will be able to make the thicknesses vary, modify independently. In the mesh module, okay, we have seen that we have meshed our structure. In the interaction module, we can see the 4 couplings and the ref point. In the load module, we can see the boundary conditions behind, and also the gravity applied to the wall model. Also, to finish, 2 forces, Fx and Fy, the forces of the pump, and applied right at the center of the gravity. Going back to the interaction module, in Special Inertia Manager, we can also see that we have added a mass, which is the mass of the pump, applied right at the center of the gravity. So now let's have a look at the results. So we go in the visualization module. So we have our structure, and we'll click on plot contours. So the output is the von Mises stresses. So we can read here the maximum is 883. So we have to be careful because it is an average. I remember that we have seen that the maximum on our current model was about 965, something like that. So first of all, I will remove the average computation. Now we have 1000 something, but there is another trick. So first show location. So this is at this node, but the stresses are exact, calculated exactly at the integration point of the element. So to know the exact value, we have to probe S Mises at the element, and right at this one, when I click, I can find the 4 stresses values at each integration point of the element I have selected, and the maximum of those values is 963.6. So exactly what Eyesight will find, because I have told around 965. It's exactly the maximum value of our current model, which overpasses the yield strength of our steel. Let's switch to Eyesight. Isight Design Gateway, by the way, the software I will use for this optimization problem. So I won't explain all the interface of Eyesight. I will just pick the components I need for this particular problem. So first, I go in Application Components, and I see there is an Abaqus component. So I will drag on the scheme, and I will edit this Abaqus component by double-click on it. And here I see I can browse a file. So I will read, in fact, my INP file, jobs pump support INP. And this is to be able, in fact, I will read the file, to find all the parameters Eyesight has found. We do not forget that we are interested in the thicknesses, so I will select the longitudinal stiffness thickness, the main plate thickness, and the transversal stiffener thickness. Those are the 3 parameters, the 3 input parameters I want. And you can see just next to them, next to the name, the value, the current value, 5 and 10 millimeters, because we are working in millimeters. If I go now in parameters, I find my 3 input parameters. The mode here, you can see the mode has been automatically chosen as an input parameter. So Eyesight can detect this automatically. We just change the name, so here it's longitudinal stiffener thickness. And it is right here that we can choose, in fact, the allowed values for our parameters. So for the main plate, remember that it's not a continuous range, but it is a discrete set of range, and it goes from 10 to 20, and the increment is 1. So I can add this. So we have our discrete interval values for the main plate. We do the same for the stiffeners. It goes from 5 to 15, increment 1, and I add this. And the same for the longitudinal stiffener, from 5 to 15, increment 1, I can add this. Okay. So we have defined the range of allowed values for our 3 inputs parameters. What we will do next? Let me edit the Abaqus component another time. And now I will, in fact, so in execution, I will just show you quickly, we can modify the command to launch the Abaqus jobs, because Eyesight will launch a lot of Abaqus jobs with different thickness values, and to find the best one, in fact. So by default, it is this command that Eyesight will launch, and we can modify it. Grid, I won't use that, and output. So automatically the ODB file has been added as the file to read as output, and of course I will read the ODB file into Eyesight, because do not forget I want to use as an output parameter the von Mises stresses or stress maximal value, and I will find this one in the ODB file, and Eyesight enable me to find all the parameters I can use, and step 1, S Mises max, this one. I check it, and I will just see the value. Yeah, it's 963.6, so exactly what we have seen together. So okay, I go back to process component, and I do not want to establish a kind of task, but I want to optimize. And for optimization, I have a component which is called optimization in Eyesight, and I will replace the task by an optimization. And I want to change it, yes. So now I have an optimization. So I will edit this optimization component. First, I want to see in the data flow if I can link optimization and Abaqus. So Abaqus here. So for instance, you know, I have to drag like this. So it goes from optimization to Abaqus. So it is exactly input parameters for Abaqus, but they are output from the optimization component. And this one, I think it also goes to optimization, and it is an input for optimization. So the arrow is in the other sense. You see, we have 3 input parameters. Goes, the Abaqus job runs, and we have the von Mises stress that will goes into the optimization component, which one will change, modify the 3 parameters, and etc. So that's why we have seen we have input and output data. And now I go in my component, optimization component. I can edit it. And first we have to choose our optimization technique. I'll choose the pointer one, which is very general, very robust in Eyesight. And I go on variables, so in it we can find back our 3 input parameters for the Abaqus job. So I will say that all are variables for my optimization problem. We have allowed values that have appeared. In objectives, The main objective is to have the maximal von Mises stress close to the target we have defined before together during the presentation, 335. This is our objective. We want the pump support to withstand the stresses and not to be too oversized. In the constraints tab, we will activate our Mises maximal output variable, and as an upper bound we do not want to overpass the yield strength, and as a lower bound, like we said before, we do not want to go below this value, 245 MPa. Okay, and so we have defined our problem. We have defined the allowed values for our 3 input parameters. We have defined our optimization problem. The only thing that remains is the fact that we do not want to compute when the thicknesses of the stiffeners, longitudinal or transversal, are greater than the thicknesses of our main plate. And we can implement a rule in this arrow just before the Abaqus job, conditional execute, and we can call this condition inequality. And inside this inequality, I will just see the parameters we have. And so we want that the thickness of the stiffener, so the first stiffener, remains lower or equal to the thickness of the main plate, and is the same in fact for the other one. So this one lower or equal to the thickness of the main plate. So we have the longitudinal stiffener and the transversal stiffener. Okay. Okay. So here we have a conditional execution of the job inequality. If it is not satisfied, the Abaqus job won't run and we do not lose any time. So now everything is set for us to be able to launch the Eyesight computation. So we click on Run the model, and in fact this will launch a second software, Isight Runtime Gateway. And the calculation will effectively give several lines like a table. We will see together that Isight has a color code that will enable us to find the best result. Okay, and after several minutes or several hours, depending on the size of your Abaqus model, Isight gives you his verdict, and each line corresponds to an Abaqus calculation. And we can see a synthetic view of each result. When the line is red, it means that a constraint has been violated, so the result is not acceptable. When a line is white, it means that the result is acceptable, feasible, but it's not the best one. And so we go down, we have a lot of calculation, and you can see among all the white lines we have a green line, which represents in fact the best result found by Isight. And you can see he has made a lot of calculation, 166 calculation, and I am happy not to have done that manually. Isight did it for me very well, and that is the point I wanted to show you. And so this calculation seems the best, so I can just reduce the number of parameters displayed, and it was this line, 114. This calculation is the best one for Isight because we get a von Mises stress at 333.5, very close to our target of 335. And the couple of parameters enabling that are for the main plate 17, for the transversal stiffeners 15, and for the longitudinal stiffeners 10. Would you have been able to find this by yourselves? That's great that Isight give that for us. So I found my optimized values. I'm happy with that. I hope you enjoyed this video on Abaqus and especially Eyesight. See you next time. Bye.